B is changes from 0 to 1. So you can see that essentially this is slightly faster than the carry bypass adder, because in carry bypass adder we needed 12 units of time to generate the sum, whereas here we require 10 units of time. Okay. Do all of you understand this? Can you raise your hand if you have not understood? I'll repeat it. Okay, good. What don't you understand?
Why don't we just calculate the sum and carry output at the same time? We can also predict the carry B for the sum logic.
Do that again.
I mean, can we predict the carry B for the sum logic and then generate the sum and we
At the same time?
with the carry out B?
No, because what is sum? Sum is equal to P exclusive or CI, right? P is A exclusive or B, correct? Now this CI is the output carry from the previous stage. So this has to come from the previous stage. Before that we cannot generate. So here it has to wait and then select one of these. Here the carries have been generated, but multiplexer cannot send it over here because it will be giving the wrong value. It has to wait to find out what the value CIO over here. We should be selecting one of them, and then you can generate. You follow? What is sum? Sum is equal to A exclusive or B exclusive or C in, right? What is A and B? A and B are coming from here, which is the propagation function, right? So that is passed over here. You follow? But we don't know the value of CI because it is coming from the previous stage. So that's why it has to wait. Am I clear?
Why don't we just assume that the carry will be 0 or 1 and calculate the sum before the real carry arrives?
That's what it is doing, exactly what you're telling. Basically, it is creating two different chains, 0 carry chain and 1 carry chain. Okay? But we don't know which one to be selected because we don't know these things sitting here. Once this is generated, then we can select, okay, here we find out that the carry out is selecting the, so look at this one. So basically, B is 1, 1, 1, and A is, first bit is 1 and the rest are 0, right? So the sum will be propagation multiplied by the carry input here. The propagation function is 1 and carry in is 1, so the sum is 0. Similarly, propagation, then the carry input coming over here, the sum is 0. Then propagation and carry input is 1, sum is 0. So that's how the sum has become 0. You follow? Now, here, the carry out is 1. So this carry out is 1 will be selecting the value corresponding to 0 carry. So that's how this is 0. So this is how they're getting selected. Yeah.
For the first set, it's 0 through 3. Why do you have to do the preemptive select? Why can't you just put in the CN?
Do that again.
So for the other stages, you have to wait for the CN, but for the first stage, why can't you just start from where the CN comes in?
That's what I'm doing.
But it still does the setup and the two possibility computations, right?
Yeah, but the thing is that each of these is a triple carry adder.
Mm-hmm.
Each of these blocks are triple carry adder. Okay.
Yeah, you mean in the carries?
This triple carry adder is taking the value of the setup value and then assuming the carry input is 0 and setting up the value.
Yeah, so I'm saying for the first block, why does it have to assume it? It can just take the CN, right?
Oh, you would say that here,
Yeah.
in your design here, but this is just a,
Oh, okay, okay.
it's just a, a segment of the design, how it works.
But again, I'm sorry, the first section.
Sure. I mean, in the first one, you can, but the thing is, what you do is that you make them, so your point is that why do you have to make 2 of them and why do you have to put the multiplexer? I can reduce the time by having one chain and then taking it out. Fine. But this example is basically to generalize way, if you look at the segment, what it is like.
I understand.
You follow?
Yeah.
Any other question? Did you not, I mean, can you explain to everybody what you asked and what you understood?
Yeah, so I asked, that you create the 2 possibilities for the carry in to preemptively check so you can parallelize those functions. But with the first stage, you don't need to create the 2 possibilities because you immediately have the carry in from wherever it's coming from.
So what he's telling is that I don't need 2 different chains, I don't need the multiplexer for the first stage. I can have just one triple carry adder block and I can use those values some generation and rest of them can be like this, right?
Yeah, and then I think you gain 1 time.
Yes, that's true. But I'm just showing the principle, that's why we have made everything uniform, okay? So, if I try to optimize so this is the expression for the carry select adder. Now, if I try to optimize the value of m, you will find out that it's different from the previous case. In the previous case, it was square root of m. In this case, I can increase the size in this particular example by 1 bit. So this is a 2 bit, this is 3 bit, this is 4 bit, this is 5 bit, and so on. Okay. So that comes from the fact that if you use the p stages, so first stage adds m bit, and then we assume that there are p multiplexers, p stages, and each of these are m plus 1, m plus 2, m plus 3, like that, right? Then I see that it forms an AP series, and we can estimate the value of p square root of n. So, in order to optimize the size of the carry chain as well as the number of stages, we can do it in 2 different ways. We can linearly increase it, like in this case. First stage is 2 bits, second stage is 3 bits, 4 bits, 5 bits, and so on. And we find out that the delay, you can calculate 1, then 4, and 8, and so on. So this is better than the previous example. But if I use this particular little mathematical optimization, then I'll be using first one m bits, and then I'll use p, which is square root of 2n, number of stages. So that is called the square root select adder. So if I do that, what I find out is this, that if I select linearly, sorry, I think I just messed up a little bit here. The idea is like this, that first one is 2 bits, then 3 bits, 4 bits, 5 bits, and there are such stages, and p is equal to square root of n. And this is what we will call the square root select adder. So that is like this. So you can see that the first stage is having 2 bits, then 3 bits, then 4 bits, then 5 bits. So it keeps on increasing subsequent stages. And we use this by using the formula p is equal to square root of 2n. So the delay will look like this. But if I don't do that, like I do not change the size of the blocks, I keep all the blocks the same sizes, like in this case, the 4-bit wide, then the delay will look like this. It will be increasing step by step, and it increases faster than the square root select adder. So here the value of the m is constant. That's why we call it linear select adder. And in this case, the value of m is changing by using that formula. And as the number of stages increases, the width of n increases from 2, 3, 4, and